Hello students, welcome to lecture 28 of the online course on Nanophotonics, Plasmonics and Metamaterials. Today's lecture will be on metasurfaces and frequency selective surfaces. So here is the lecture outline. We will look into the basics of metasurfaces, their application towards phase modulation and some other applications, and then we will move on to frequency selective surfaces. We will see their definition, we will look into the fundamentals and also discuss their applications. So, metasurfaces, when it comes to mind, it is basically a two-dimensional metamaterial with sub-wavelength periodicity, and these metasurfaces are able to demonstrate unusual electromagnetic properties, and it can vary over a frequency range from microwave to terahertz to optical. There are resonating metamaterials which can be tailored by tuning the geometry of its unit cells or metaatoms. So, conventionally they are used for phase change and focusing of electromagnetic waves at optical frequency in the far field region. So, here is an illustration of typical metasurface. So, you see it is a very thin, it is a basically 2D material with all these unit cells which are basically working on the phase of this incident terahertz wave. It can be terahertz, microwave or optical depending on the frequency range you are looking at. But what it can do, it can modulate the phase or the amplitude or the polarization. Okay. So, that way you can actually get polarization modulation, spatial beams, active control, focusing, hologram. Okay. All these different things can be generated by using metasurfaces. So, a formal definition for metasurface is basically an ultra thin array of sub wavelength scale metallic elements which are deposited in periodic, aperiodic or random patterns on the surface of a dielectric substrate. And the shapes of the individual elements and their geometry of the layout on the surface, they endow the metasurfaces with distinctive optical properties. And if you think of the origin of these spatial effects that comes from the metasurfaces, they are basically a consequence of coupling of light and the surface plasmon propagation waves that generate at the metal dielectric boundary. So, today we will look at a comparison of metasurface with metamaterials. So, if you remember metamaterials, they are basically 3D materials which are able to provide artificial permeability and permittivity. So, if you remember the split ring resonator array positioned on a metallic wire, that was able to give you negative permittivity as well as negative permeability. So, what we do, we can actually model the system as an effective permeability, mu effective or epsilon effective. So, this is typically a 3D version, okay, that is the periodic cells, the unit cells are repeated in periodic fashion in all 3 dimensions. Okay. On the other hand, you can think of metasurface which is basically a 2D version. So, here the periodic arrangement of unit cell happens in 2 lateral dimension. The thickness is very little. So, how it can help? So, it can actually change the amplitude, frequency, polarization or phase of the incident wave. So, here is an example, say if right circularly polarized light falls on the metasurface, it may give you a left circularly polarized light. Okay. You can also think of left circularly polarized light falling and some part of it getting reflected. So, it is blocking the left circularly polarized light to go through. Okay. So, this kind of applications may be possible. So, let us look into the basics of how phase modulation can be obtained through metasurfaces. So, let us assume a wave that is travelling along the z direction as shown in the figure, okay, and on the transmission through a dielectric plate of fixed thickness, that is d, okay, and graded refractive index. So, the refractive index is given as nxy. So, it is in the xy plane. Okay. So, this is z direction. Okay. So, the xy plane is basically the vertical plane. Okay. And in that case, the wave will undergo a spatially varying phase shift, which modified its wavefront. So, you can write the phase shift phi xy as nxy k naught d. So, here you can see this is the free space wavelength. As soon as it enters a medium with a refractive index say nxy, so the wavelengths get shorter. Okay. So, you can see the periodic, the wave looks compressed. When it comes out, it again retains the same kind of wavelength, okay, in vacuum. So, here the variation is in xy plane. You are seeing this is the z direction. Okay. So, this is how it changes. Now, achieving a phase shift of 2 pi requires a local thickness which is equivalent to the wavelength of the light in that medium. So, that is how you can actually get a phase shift of 2 pi, right. So, d has to be equal to lambda in that particular medium. Now, a planar metasurface has the merit that it can introduce a phase shift of similar magnitude with far less thickness, and this is where things become interesting. That the same amount of phase shift can now be achieved using metasurface instead of using this dielectric plate. You can use a very thin metasurface which is only couple of nanometers thin, okay, and still you can get a similar kind of effect. Normally lambda in optics, it is like in micrometers, okay, orders of micrometers you can think of. Okay. So, if you think of telecommunication wavelength, it is 1.55 micron. So, in that case, to achieve 2 pi phase shift, you will require lambda thickness of this material. Okay. So, that is typically 1.55 divided by n, that will be the lambda in this particular case, but that is still also in micrometer range. But metasurface can help you achieve that with a nanometer scale thickness. Now, what is the magic in this metasurface? So, the metallic elements that you see in the metasurface, that function much like optical antennas, which can modify the optical wavefronts. So, when you think of resonant antennas, they act as scatterers and they can introduce a frequency dependent phase shift, which can range from minus pi to pi for the frequencies below and above resonance. So, a spatially varying phase shift like phi xy may be implemented by making use of a metasurface which comprises elements of spatially graded size, because along x and y there is a variation in the phase shift. So, the elements need not be same along x and y, you have to change their size and geometry, so that you are able to get spatially varying resonance frequencies. I will explain this with example very soon. So, an incoming wave of fixed frequency is then subjected to this spatially varying phase shift, so that the metasurface can now act as a phase modulator. So, let us take this particular example where the metasurface is basically an array of metallic elements. So, all these elements that you see, these are metallic elements. So, the metallic elements, the element size and geometry are same along the y direction, but along z direction they are different. Okay. So, that way the phase will be changing along the x direction, right. So, the phases, so this is just an example of how you can change phase along one particular direction. So, here you can see the shapes of the elements are engineered such that the phase shift they introduce becomes a linear function like phi equals qx for one of the polarization components. So, here it becomes a linear function along x. Now, since these metasurfaces are ultra thin, they can be modeled as optical components that introduces a spatially varying phase shift, or you can say phase discontinuity, because a phase shift that takes place over a distance d equals 0 can be thought of as a discontinuity, and the thickness of this metasurface is like almost 0. So, you can say that they introduce spatially varying phase discontinuities. Now, what is the benefit? By doing phase modulation from these metasurfaces, you can actually modify the incoming optical phase front. Okay. So, like this you have seen, you can use in the same manner, like plane transparent plates, they may allow the light to simply go through without modulating the phase front, but when you take prism, you can actually send it at a particular angle, okay, depending on the prism angle alpha. So, all these functionalities can be achieved. Not only these two, the work of a lens which does the focusing at a particular focal point at a distance f, or diffraction grating, or graded index plate which also does focusing kind of application, all these components can be literally replaced by metasurfaces. So, the design of the constituent elements need to be changed depending on the application. So, this is what a salutary feature of this approach of using metasurface is, that the wave will undergo minimal spatial spread or diffraction as it crosses the infinitesimal small metasurface. So, this is a very good benefit of using metasurface, because the thickness is almost 0. So, it will have very minimal diffraction, or you can say minimal spatial spreading. So, that is why people are trying to replace all these bulky optical components using these ultra thin metasurfaces. Now, let us look into how this phase modulation works. So, let us consider a phase which is phi xy that can vary linearly along this metasurface at a rate q. So, q is nothing but the rate of phase change. So, you can write phi equals qx, because in this case it is only changing along x direction. So, this is the same metasurface that you have seen before, right. So, it is changing only along x, along y it is same. Now, the complex amplitude of any incoming wave can then be modulated by a factor exponential minus jqx. Okay. So, this is the phase that will be coming into the picture. So, which is basically a periodic function of the spatial frequency Vx, that is q over 2 pi. So, this is the spatial frequency of those elements, okay, that introduces this phase. So, now look into this figure. So, this figure basically shows a negative reflection and negative refraction at the boundary between the two media of refractive index n1 and n2, okay, when the metasurface is basically present at the interface. Okay. So, here an incoming plane wave of wave vector k1, which has got an incident angle of theta 1, okay, and it will generate a refracted wave with wave vector k2, but it is basically a negative refraction. So, instead of going that side, it is basically coming towards on the other side of the normal. So, the angle here is theta 2. Similarly, some part of the incoming wave will be reflected back, but here also we are considering negative reflection. So, k3 is the reflected wave vector and the angle of reflection is theta 3. So, what has to be done for this wave to exist, or this condition to exist? You have to go through the phase matching condition for the incident and refracted waves, as well as for the incident and the reflected waves at the metasurface boundary. So, this is the metasurface boundary, and you can see that all the wave vectors are drawn here. Okay. So, this is k3, the reflected one, this is k2, the refracted one, k1 is the incident one, and this is the vector of the phase change. Okay. And this is n1 k0, that is n2 k0. Okay. So, now to ensure the phase matching at both sides of the surface, as we have seen in this figure, what we have to do? We have to look for the component of the vector k2 parallel to the surface. So, that will be basically the sin theta component, right, and that should match the same component of k1, the surface parallel component of k1, that will be again the sin theta component plus that q vector, okay, and q is basically the vector of magnitude small q that points in positive x direction or in the x direction, because it is changing in x, okay. So, you can take it like that. So, if you do that, you can actually put that for the reflected wave, you can do the similar kind of exercise, which is basically you have to look for the parallel component to the surface, that will be the sin theta component. Here theta will be theta 3, okay, and that should match your k1 plus q, okay. So, this way you can actually obtain the conditions and find out the phase matching conditions. So, hence if the metasurface lies at the boundary between the two ordinary medium of refractive indices n1 and n2, its presence can cause the conventional Snell's law of refraction and reflection to assume this particular modified form. So, as I was talking about the phase matching, so here you can see what is happening. So, n2 k naught, that is basically your k2, okay, the sine component, that is sin theta 2. So, that is the component of the refracted wave parallel to this surface, that is same as n1 k0, that is nothing but k1, and its parallel component to the surface, that is sin theta 1 plus q. Similarly, for the refracted wave you can write n1 k0, that is basically k3 sin theta 3 equals n1 k naught, that is k1 sin theta 1 plus q. So, this is how you are actually adding this particular factor q in your reflection and reflection equations. So, these are the metasurface refraction and reflection equations. So, these are basically modified Snell's law, where you have introduced your particular design parameter into this law. So, here we have already discussed theta 1, theta 2, theta 3 are basically the incidence, refraction and reflection angles, and by appropriate choice of the magnitude and sign of q, okay, you can actually make this work like a negative refractive or negative reflection as well as negative refraction kind of surface, as we have considered till now, okay. So, this is how a metasurface is able to get into the Snell's law and allow you that modification of the refraction and reflection characteristics. And as you can see in these equations, when you put q equals 0, that means along the x axis there is no change in the phase, that means it has become a normal dielectric material, q is 0, this goes back to normal Snell's law. Now, you can also write, so if you take this k naught on the other side and n2 you can write as nt, that is the transmitted one, n1 you write as ni, that is the incident one, and theta 2 is basically, theta 3 is basically the, you can see here theta 3 is basically the reflected angle. So, you can write a different notation, something like theta r, okay, and theta I for the incident angle. If you use this kind of notation, so here you are dividing, so you are taking this term on the left side and taking k naught common and send it on the right side. So, what you have, k naught can be written as lambda naught over 2 pi, and q, that is the rate of phase change, can be written as d phi x over dx, because only along x your phase is changing. So, this is also another form of this modified equations, okay. So, here you can see the generalized Snell's law of refraction. So, this is one medium, this is another medium, and there is a metasurface that you can see here at the boundary, Okay. So, depending on how you are designing Q, you can actually make it work like ordinary surface, where you will have ordinary reflection and ordinary refraction, or you can choose the amplitude and phase of Q in such a way that it can give you anomalous reflection, the red line, or anomalous refraction, this is the red line again. Okay. So, it depends on the design of the metasurface whether you can get a ordinary reflection refraction characteristic or some extraordinary thing. Anomalous means which is not the normal one, okay, something opposite to the normal one. Fine. So, here Q, as I told you, this is basically the gradient of the phase discontinuity along the interface, okay, and this is where the meta atom design comes into picture. So, this is given by the meta atoms of the meta surface. So, these equations also tell you that if there is no change, this part becomes 0, it is a typical Snell's law. So, you can actually make them go in any particular direction depending on whatever is the value here. So, if you choose a suitable constant gradient for the phase discontinuity along the interface, that is whatever you will choose your d phi over dx to be, you can make the refracted or the transmitted and the reflected wave to go in any direction. Okay. So, you get a complete control on the direction of reflection as well as refraction by introducing this d phi over dx, that is the Q, and that is how metasurface is gaining so much of attention, right. So, for a phase discontinuity phi x that varies slowly with the position x, you can say that the derivative may be regarded as a local spatial frequency. Okay. So, this quantity also determines the local tilt imparted on a incoming wave, and thus the angle of reflection and refraction also becomes a function of x. So, this approach can be clearly seen to be generalized to metasurfaces that introduces a two-dimensional phase discontinuity. So, right now we just saw one example of one-dimensional phase discontinuity. You can actually make it 2D, and that gives you that phi xy. So, in that case the Q vector will be basically the gradient grad of phi, okay, and this vector represents the magnitude and the direction of the local spatial frequency of the phase modulation. So, that will determine which way the reflected and transmitted wave can travel. Okay. So, here is the summary of the metasurfaces. So, we understood that the metasurface can be designed to introduce desired local tilts in the wavefront of the incoming wave in both x, z and y z planes, much like the antenna array or an optical faceplate. Okay. So, the metasurface can be engineered to introduce position dependent amplitude modulation, which can be imparted by the shape of the local elements or the meta atoms, and the combination of phase and amplitude modulation can serve as a hologram with complex transmittance that is designed to simulate the wavefront of light generated by an object. So, here are the main understandings of this metasurface. So, we understood light propagation with phase discontinuities, which are basically introduced by metasurfaces. Now, by engineering a phase discontinuity along an interface, you are able to fully steer the light wavefront and accomplish some unparalleled control of anomalous reflection and refraction, which is described by generalized Snell's law. Okay. So, we will take some example here. So, as shown in the figure, so you have got a V-shaped resonator. So, there are two ways light can fall. One is this S, that is this particular direction, we can call it as a symmetric direction, or A, that is asymmetric direction. So, when light falls or the electric field is along this S vector you can excite symmetric mode on the two branches of this V shaped resonator. The angle is 45 degree, okay, and what you see here is basically the current distribution, which is represented by the colors, okay. So the blue line shows current distribution for the symmetric case, the red one shows for the asymmetric case, and the brighter the color, larger is the current, and the current flow direction is also shown here, okay, through these arrows. Now in this case what happens, you can also take mirror image of this particular antennas, and they also do similar kind of properties, and you can get the components of the scattered electric fields, just that they will be pi phase difference from this one. So just by rotating the antenna you can create a pi phase difference, okay. So in the symmetric mode, if you look into the current distribution in each arm, okay, it approximates that of an individual straight antenna of length h. So this is length h, okay, and therefore a first order antenna resonance can occur at h equals lambda effective by 2. So what is lambda effective? That is the effective wavelength. So in symmetric mode, h equals lambda effective by 2, whereas when you go for antisymmetric mode, okay, so antisymmetric mode, this is the direction of the electric field, okay, it is along this a axis. So you can see the current distribution is actually, okay, in the entire arm, okay. So in that case the total length is 2h, and that is equal to lambda effective by 2, okay. So you can also say that the current distribution in each arm approximates that 1/2 of the straight antenna of length 2h that you can see here. So here the overall length, antenna length is 2h, and the condition is basically 2h equals lambda by 2, okay. So this is how the symmetric and antisymmetric modes will operate differently, okay. So you can also see the analytically calculated amplitude. So this is basically the amplitude shift, and this is the phase shift. So this is different length, or you can say height h of the antenna, and these are the different delta angle, that is basically the opening between the two arms, or you can say the angle between the two arms, okay. So what we are seeing here, so analytically it has been calculated what happens to the amplitude and phase shift of this cross polarized scattered light by this V antenna. Now if they are made of gold rods, so gold rods, they are basically having cylindrical or circular cross section. So if you see, take the cross section, they are basically circle. So these are rods, okay, and their height or length h is varied, and the angle is also varied, and the wavelength is kept fixed, lambda naught equals 8 mm, okay. So what happens in this case? So you see the 4 circles, okay. So these 4 circles basically show that you are basically changing the angle, okay, between them. So the optical property of the rod of the same length, so here you are keeping the length same, but you are changing the angle between them, and you are comparing it with a flat antenna of the same length. So you can see how the amplitude as well as the phase changes, okay, in these two cases. So here the blue and the dashed curves, they correspond to the resonance peaks of the symmetric and antisymmetric mode. So symmetric mode is this one, sorry, this one, antisymmetric mode is this one. So we are only talking about like this particular case, so you can only think of the top case, not the bottom one. But then if you look at these 4 antennas, what is happening here, you also correspondingly see the phase pattern. So when they are detuned from the resonance peaks, okay, as indicated by the circles in C. Here you can see these circles. Okay. You can see that there is a incremental phase shift. This guy is having 90 degree, then you have 45 degree, then you have 0 degree, and then you have minus 45 degree. So, this is how the phase of the cross polarized scattered light is changing by changing only the design of the elements. So, if you start opening up these antennas, so this is a V type of antenna, and then you start opening them up, you will actually get incremental phase of pi by 4 getting changed from this design to this design. Now, if you do the mirror structure, that is this one and this one, okay, you can actually get additional pi phase shift introduced. So, you actually got many elements which can give you your desired phase shifts. So, this is evident by observing the currents. So, because they too have completely different current pattern, obviously they are 180 degree out of phase, or you can say pi is the phase difference between this one and this one. Okay. So, if this is giving you 45 degree, this will give you 45 plus pi, okay, like that. So, with that people have done some experiments with the metasurface. So, this is a set of 8 antennas that has been taken, but you see there are basically 4 antennas and then they are repeated. So, this is how the antennas are taken, and then you take this as a unit cell and then you repeat it. So, this is an SEM image of the antenna array which is fabricated on a silicon wafer. The unit cell is basically these ones which are highlighted in yellow. These are all gold V shaped antenna. The width is 220 nanometer and the thickness is 50 nanometer, and the repeat period with a periodicity of 11 mm. Okay, so that is the periodicity in x direction. So, this is x direction, horizontal one. So, the periodicity is 11 mm. Okay, the whole thing repeats like that, and along this direction, along the y direction, you have 1.5 micrometer as the periodicity. So, these antennas are designed in such a way that they have equal scattering amplitude. So, each of them will scatter the same amplitude, but they will have a constant phase difference of pi by 4 between the neighbors. From this one to this one, pi by 4 difference, from this one to this one, pi by 4 difference, and so on. So, let us see what is the purpose of doing this. So, if you look into the simulation study, so this is the 8 antennas that you have seen. Okay. So, they are basically created from these 4 antennas repeated again. So, you can also see that their amplitude is pretty much same, just that they have a phase that increments as pi by 4. So, this is the silicon substrate on which the antennas are kept. So, this is the point where the antennas are placed, and you can actually see that when this particular plot shows the scattered electric field which is polarized in the x direction for a y polarized plane wave excitation at the normal incidence from the silicon substrate. So, this is the silicon substrate part, and it is located below this z equals 0 line. And another important thing to notice here is that the antennas are equally spaced at sub-wavelength separation of gamma by 8, where gamma is basically the length of the unit cell. So, total length is gamma. So, you have equally spaced them, okay, and this is how the spacing is 0, gamma by 8, gamma by 4, 3 gamma by 8, and so on. Okay. Now, what happens if you draw the phase front? Okay, you will see that this particular tilted red straight line shows you the envelope of the projection of the spherical waves that are scattered by these antennas onto the xz plane. Okay. So, that way you are able to see that you are actually able to steer the beam. The beam, normally it would have been this black dashed line, but because they are incrementally adding pi by 4 phase okay, you are able to tilt the beam or steer the beam. So, that way a very thin surface can do beam steering. Okay. So, that is only one particular application which has caught the initial attention of the metasurface or all the scientific community at large. There are other applications also like metasurface holography, metasurface polarizer, metasurface lens, sensing, cloaking, beam steering, absorber, hyperspectral imaging. I believe in the initial lectures when we were talking about the applications of metasurfaces, I have discussed all these applications in details. Now you can go back and revisit that lecture, and now you will be able to make more sense that how metasurface is allowing you to achieve all this. Now let us look into another important topic, which is frequency selective surfaces. So, when we talk about frequency selective surfaces, it is basically a periodic structure with two-dimensional arrays of identical elements which are arranged on a dielectric substrate. This kind of surfaces, when incoming plane wave falls on them, they can be either transmitted, so that is a pass band, or reflected, so that gives you a stop band, okay, which can completely block or selectively pass or something like that, depending on the nature of the element that you have put in that periodic array. Okay. So, something like this. So, what is the advantage of FSS? It can be broadband, okay. You can have it can be robust to angle of incidence, and most importantly the resonance frequency depends on unit cells shape and size. So, here you can see this is a frequency selective surface. So, only the in band frequency is allowed to pass through, all the out of band frequencies are basically getting reflected. So, at microwave and optical frequency ranges, spatial filtering is most desirable in all signal processing systems, and there frequency selective surfaces come into picture because they are called the spatial filters, as they are used to modify the EM wave incident on such surfaces, and then they can provide dispersive, transmittive or reflected characteristics. Now, how FSS are designed? FSS are typically designed by periodic metallic arrays of elements placed on a dielectric substrate. The change brought to the transmitted waves can be both in amplitude or phase when you compare it with the incident wave, and in any case the selectivity may be introduced against the incident polarization to improve the irregularities in the emission pattern, which is exhibited through a change of the phase or amplitude of the transmitted wave. Now, there are different applications depending on the nature of modification that you have done to the transmitted wave. So, some examples are, you can think of metal grid array. So, here the dark line shows the metal, okay. So, these are metal grids. Here also the dark one shows the metal grids. So, this is basically a inductive element. So, you will get a high pass filter kind of characteristics when you see the transmission coefficient. You can also make array of metallic patches. So, here the dark ones are the metallic patches. So, dark metallic patches, they behave like capacitive element. So, you can get low pass characteristics based on this. You can also make other shapes, something like plus shape, metallic plus shape. So, that actually gives you a band stop characteristics, and if you try to make a inverse structure of that, that is a complementary structure. So, you take a metallic sheet and then you make this plus shape holes punched through them, you can get the inverse characteristic of this band stop, you can get a band pass transmission characteristics. So, this is what we have seen, that typically the FSS patches, they have resistance because you are using metallic elements, and they can have inductance or capacitance depending on whatever the elements you are using. So, when you are using metallic patches, you can think of a capacitive element. So, it can give you low pass characteristics, and when you use inductive when you use metal grids, you can think of this as inductive elements, okay, and they will give you high pulse characteristics, okay. That is basically the inductive response. So, using this high pass and low pass, you can always think of, and you can combine them in series or parallel to make band pass or band stop characteristics, as you learned already in circuit theory. So, here also something like that can be used to make FSS based filters using these concepts. So, physically, when a unit cell of FSS is illuminated by a electromagnetic wave, you can convert that into a effective equivalent resonance circuit, right. So, in the case of metallic patch, it is a capacitive element, as I mentioned. Metallic grids is a inductive element, but when you try to make a metal square loop array like this, okay, so the dark one is the metallic loop. So, it can be modeled as a L loop and C loop, okay. So, there is gap between the loops that will give you that capacitance effect, okay, and this loop will give you that inductance, okay. Similarly, you can also make metal square slots. So, you are actually making slots like this, okay. So, that can give you L slot and C slot in series parallel with another inductance that is coming from this particular grids. So, that way you can actually make resonating elements, okay, and the resonance frequency of this kind of loops can be obtained as 1 f equals 1 over 2 pi square root L C. So, that will tell you where the resonance of your band pass or band stop filter will be placed. So, by choosing appropriate array element, you can choose the characteristics of your FSS. Different types of unit cell geometries have been implemented, which are very common to the FSS community. So, let us classify this. You can classify them based on their resonant properties, okay. So, you can also see that there are some elements which are non-resonant, like patch and wire grid, where you only have either capacitance or inductance, or you can also have single resonator element, something like a loop or a cross or a dipole kind of thing, which can be modeled as a series combination of inductor and capacitor. So, this will be resonating element and these are non-resonating elements. So, the classification can be done like this, the group 1 is basically center connected, as you can see, these are center connected. The length is basically kept as lambda naught by 2, okay. So, this is the overall length, as you can see here. So, here larger elements relative to wavelength. Now, in this one, the loop type, the circumference is basically of the order of lambda naught, and in the solid type or the plate type, as you can see, there are different structures, designs possible for patch. You can have square patch, hexagonal patch, circular patch, and so on. So, here the length, okay, or the length of this is kept as lambda naught by 2. So, again the larger elements relative to the wavelength, and the group 4 can be combination of any of these elements from the group 1, 2 and 3. Now, what is the main application of FSS? One important application is towards electromagnetic shielding. Now, electromagnetic interference is a very important factor because it may cause malfunction of any electrical and electronic component in a sensitive environment. Now, it is important to shield the source of interference, but that may not be the optimum solution. So, one of the most common approach is basically to shield the sensitive device, okay. And typically what people do, they apply a metal foil that can be employed as a electromagnetic shield to protect the RF circuitry from the radiated fields. Although this technology has some disadvantage because it blocks all kind of transmissions irrespective of the origin. Now, that you may not like, okay. So, in that case, FSS may actually help you from getting rid of this kind of problems. So if you design a 2D single layer FSS, they will definitely have clear advantages, because they will be easy to fabricate, and they can only block or emit a selective frequency. They will not shield all the frequencies. Okay. So those are the application scenarios. So here is a design layout of an FSS. As you can see, these are the different structural parameters. This is the period, that is periodic arrangement. Okay, this is the overall 3D view of the unit cell, and this is the side view of the unit cell. So this is basically FSS made of copper on a dielectric substrate, and it is Rogers 5880 substrate, which has got a thickness of 0.127 mm, permittivity of 2.2, and dielectric loss tangent is given here. And this is the overall dimension of the unit cell, 6.8 by 6.8 millimeter square. Okay, and dx is the parameter that gives you inter element spacing. So what I am showing here is a design of a FSS and what will be the response for that. So we are putting this parameter p, okay, on the rectangular lattice. That tells you about the periodicity of the proposed unit cell in this fabricated FSS. Then you want a resonating frequency at 10 gigahertz. So you actually optimized all these physical parameters, L, G, W, R, dx and p, all are these physical parameters. These are the range over which they are optimized, and these are basically the optimized dimensions of the FSS that has been obtained. Once you optimized, you have fabricated the FSS, and this is how the fabricated FSS looks like. So this is how you can create a measurement setup. So you can put two horn antennas operating bandwidth of say 8 to 12 gigahertz for measuring the transmission characteristics. The antennas are connected to a network analyzer, and you can actually measure the transmission characteristics by placing a FSS between these two horn antennas. Okay. And what you will see, you can measure the S11 and S21 parameter. So this is the plot of the dark line shows the transmission characteristics, and the dotted line shows you the S11. So here you can see for the 10 gigahertz, okay, it is giving you a very effective shielding of almost 56 dB. It's minus 56 dB here, you see. So it can block 10 gigahertz frequency up to 56 dB. So that is very good shielding, and it will not actually block other frequencies. So this is very good electromagnetic shield, this FSS at 10 gigahertz. Okay. So because of the design symmetry along x and y, you can say that this FSS will give identical response in both TE and TM incidences. So that makes this a very useful one. So here are the other potential applications. You can think of absorbers, you can think of filter plus antenna. So here you have receiver antenna, you can have a bent pulse structure made of FSS, and then you have a transmitter antenna. You can also have absorber plus filter, where you can have a resistive FSS here which can absorb. You can have a passband metallic FSS here, and in between there is a spacer. So these two combined can give you something between transmission or absorption. So you are switching between transmission and absorption, okay, and you are keeping the reflection more or less flat. Okay. You can also have tunable absorbers. So based on this FSS, where you can also include some of the liquid crystals. So I will not go into details of this, but these are different applications. Apart from shielding, you can have absorber, filter plus antenna, absorber plus filter, and all these things made out of FSS. So with that, we will stop here today, and in the next lecture we will consider guided mode resonance. So regarding this lecture, if you have got any query, you can always drop an email to me at this address mentioning MOOC on the subject line. Thank you.